Part 2, a quick review of Part 1. We know how to multiply, it's repeated addition. And we know exponents, they are repeated multiplication. And I don't care what you say about it, that's what I'm going to say because that gives me the right number. The right number of apples. But I couldn't solve this problem. Well, here's a hint, try this. Because exponents, that's what I'm saying, exponents are more than just repeated multiplication. Addition slides, multiplication stretches, exponents do something else. First step, get general with big gamma. And my first choice for big gamma is a special number, e. Here's a graph, and if that seems random, well, remember, my first choice for alpha was 0, my first choice for beta was 1, but then later I let them be anything. And exponents are special, they're weird. Even if these two graphs look kind of the same, at least for positive x's, and exponents and power, they can famously be made to agree. They agree famously, which can help us if we wanted to find a value for e, but we really don't. We just like e. We don't need to know too much about it. It allows us to destroy big gamma. Don't worry, he'll be back. Welcome to little gamma. Welcome to the natural logarithm, which we'll use to define little gamma. And if you don't trust me, use your calculator. Use it for x equals 2. Use it for x equals 3. Let's use it to solve this. Replace, rearrange, solve. 3 cheers for little gamma. Moving right along then with a word of caution. Here is our graph for the natural logarithm. Little gamma can be anything, from negative infinity to positive infinity, but big gamma must be positive and fine. Fine, okay if that's what you say, I am okay with that, but it's a lie. I can square negative 2, I can cube negative 2, but my calculator cannot raise negative 2 to a fractional power, which is weird. Remember these guys? They are bored and want to dance. Oh yeah. And what about this sliding, stretching stuff, and why do we prefer little gammas? Well, here's a graph for gamma equals 1, and here's another form of the same graph. This one blows up, and I can see why. This one's a bit calmer. Small gamma this time. Small gamma is a fraction. Big gamma is still greater than 1. Interesting. Negative gamma. Decay. Big gamma's turn to be a fraction. Die quickly. I liked this graph best, and right here x and y are about the same. Y, remember, must be positive even if x is negative. So what's so special about e to the power of this? It's proportional to its own derivative. So we really don't even need to know x, which is weird. If you know y, you know the steepness or the speed or the derivative at y. And that's why this guy gets so big so fast. Faster all the time. Approaching, never reaching infinity. What about negatives? Same thing in the opposite direction. Y gets smaller, and it changes more slowly, approaching but never reaching 0. Number line time, x the owl, parked at 0 because we don't really need them. No negative y's allowed. When the tiger is close, moving slower, farther away, tiger speeds up. Gamma is negative now, coming home. Closer is slower. But what kind of motion is this? A slide? A stretch? Both? I wish I could say something smarter about this. All I can say right now is that the value of y is proportional to its own slope. And if you want me to say something smart or conceptual like exponents are rotations, that's part 3. Inverse functions. Not subtraction, not division, the natural logarithm, which is easiest to see when gamma equals 1. Inverse functions. The slope of the one on the left is equal to y. It gets bigger and bigger. The slope of the one on the right is equal to 1 over x. It gets smaller and smaller. See, they're inverse functions, which is something we kind of already knew. Like we kind of already knew about this repeated multiplication thing. 1, 2, 3, 4. All right, I see it now. I'm a little bit more comfortable with this. But get on to that slide stretch connection. Well, generally speaking, 1, 2, 3, 4, look up there, 5. Addition and multiplication connected in a slide rule with log scales. That's log 2 plus log 3. It equals log 6. You already knew that 2 times 3 equals 6. Now we're saying that log 2 plus log 3 equals 6. Check it for yourself. How about the log of 3.5 plus the log of 2 equals the log of 7? Just in case you needed help multiplying those two numbers, exponents connect additional slides with multiplication stretches. Not because they are the same thing. See, it's not like they're the same thing. They're connected. Just like part 2 is connected to part 3.